So in this lecture, we will consider the Ising model in dimension 1. So remember, we defined an energy H of a configuration sigma, which depends on a configuration eta, where eta it's an element of minus 1 to the power z. Here, usually in zd, but since we are in dimension 1, in z. So we fix a configuration eta, and we consider the energy Hn of sigma, which is given by a sum of minus 1/2, a sum over all x in lambda n, over all y in lambda n, such that the distance between y and x is equal to 1, sigma x, sigma y. So this is the bulk of the energy. And then we have a boundary term. In our case, the boundary is simply the configuration eta at minus n plus 1 sigma minus n, and then minus sigma n eta n plus 1. So remember that in dimension 1, lambda n, it's simply the set minus n up to n. And so we have in the space of configuration, which, remember, I'm representing by omega n. So omega n is minus 1 to the power lambda n. And the configurations of, or the elements of omega n are represented by sigma. So we defined this energy. Mind that this energy depends on the boundary condition, eta. Once we have this, we define a measure, a probability measure on omega n. This probability measure will be represented, say, by beta n of sigma. And here, beta is the inverse of temperature, so it's a fixed parameter. And this measure is given by minus beta times h eta n of sigma divided by a renormalizing constant, which is Zn eta of beta. And so this is the constant which makes this measure a probability measure. So Z eta n of beta, it's simply the sum over all configurations sigma in omega n of minus beta h eta n of sigma. So this is the basic notation which was introduced in the previous lecture. And what we want to prove today, so let me say theorem. The theorem says that for any beta larger than 0, so at any temperature, if you consider what is the probability measure and this, which is called the Gibbs measure. So the probability with respect to the Gibbs measure that the spin at 0 is equal to minus 1, this converges to 1/2 independently from the boundary conditions. So more precisely, we have that beta n, so the probability that the spin is equal to minus 1. So this probability, as n converge to plus infinity, so in the thermodynamical limit, in the limit in which this box increases to z, this will converge to 1/2. And this happens for all configuration eta in minus 1 to the power z. So this is what we want to prove today. So this means that if you consider your box between minus n and n, you place here a boundary condition, whatever boundary condition, then you look at the spin at 0. Well, this spin will not be influenced by the boundary condition. So if you put a plus boundary condition, you can easily check that the probability that sigma 0 is equal to -1, it's less than 1/2 for all fixed n. But as n increases to infinity, this probability will converge to 1/2. This means that the origin will not feel the influence of the boundary condition on the measure, and this happens at any temperature. So this is the main result of this lecture. So I just rewrote the statement of the main theorem of this lecture for any beta and any eta, any configuration of -1, 1z. The Gibbs measure at inverse temperature beta and with boundary condition eta on the box -n. Well, under this measure, the probability that the origin has spin equal to -1 will converge as n tends to infinity to 1/2. And this theorem, the proof of this theorem, is based on the following lemma. So remember that we represented by z, eta, and beta the partition function, which means this is the constant which turns mu into a probability measure. So this is the sum over all configurations in omega n of exponential minus beta h eta n of sigma. And my claim is that the limit, or more precisely, Zn, so the claim is that Zn eta of beta can be written as exponential beta plus exponential minus beta to the power 2n plus 2 times a constant alpha n, where alpha n converges to 1/2. So this is our first claim. And the proof of the theorem will be based on this identity. So we claim that the partition function in dimension 1 can be written as exponential beta plus exponential minus beta to the power 2n plus 2 times alpha n, where alpha n, it's a sequence of positive real numbers which converge to 1/2. And, well, the proof requires some reorganizing the energy, the Hamiltonian h, eta, n of sigma. So remember that this, it's given by minus 1/2, the sum over all x in omega n, but in lambda n. But lambda n, we have seen, it's the box minus n up to n. Then we have here a sum over all y in this same box, lambda n, where y minus x, it's equal to 1, of sigma x, sigma y, and then the boundary terms, which are minus sigma minus 1 eta minus n plus 1, minus sigma n eta n plus 1. So this is the definition of the Hamiltonian. And now what we will do is we will just observe something I mentioned already, is that, well, here's the box minus n, and mind that what we are doing is that we are summing over all x, and then over all y, which are nearest neighbor of x. So I want to fix here a bond, which means a pair z plus 1, and observe that in this sum, sigma z plus 1 with a minus sign will appear, right? Because here we are summing over nearest neighbor. But what I claim is that if I fix z and z plus 1, that this bond, so this expression, sigma z times sigma z plus 1, appears 2 times in this sum. It appears 2 times because I can take x equal to z and then y equal to z plus 1 here, or I can take x to be z plus 1 and y to be z. So this means that for each bond, the contribution sigma z plus 1 to this sum will appear 2 times, which means that this, with this 1/2, it will cancel the 2, and this means that I can rewrite this Hamiltonian as minus the sum over all bonds. So the bonds come, so here we are taking only the bonds in lambda n, so for which z and z plus 1 belong to lambda n. So this means that the first bond it's minus n plus 1, and the last bond will be n minus 1 n. So this is equal to the sum for z going from minus n to n minus 1 of sigma z plus 1. So this sum, it's exactly equal to that one, and then we have the boundary terms, which I rewrite again. So this is minus n plus 1 sigma minus n minus sigma n eta n plus 1, and these are the two boundary bonds. So the bond between minus n and minus n minus 1, and the bond between n and n plus 1. So actually, the Hamiltonian can be written as a sum over all bonds which intersect the box minus n. And it is with this expression that we will be able to prove this identity. So I just rewrote here the expression for the energy, the Hamiltonian, and now we can start proving this identity. So by definition of the partition function, this is equal to the sum over all configurations in omega n of the exponential minus beta times the energy. So you see, when I take minus beta times the energy, the minus will cancel, and I'll get an extra beta. So this is beta, the sum in z. Let me not write that the sum is running from minus n to n minus 1, but let's keep that in mind. And we have the boundary terms plus beta eta minus n plus 1 sigma minus n plus beta sigma n eta n plus 1. And you see, we have a sum, so I can represent this sum as sigma in omega n, and here I will write a product. So maybe let me first start with this term. So I have exponential beta eta minus n plus 1 sigma minus n, then a product from z from minus n to n minus 1 exponential beta sigma z plus 1, and then exponential beta sigma n eta n plus 1. So I just rewrote these expressions in this way. And now I will consider, so let me erase the claim to have some space, and I want to consider now a Markov chain between minus 1 and 1. So this is a discrete time Markov chain, and while you are at minus 1, you may jump to minus 1 with probability exponential beta divided by exponential beta plus exponential minus beta, or you can jump from minus 1 to 1 with probability exponential minus beta divided by exponential beta plus exponential minus beta. And the same thing happens at 1, which means that if you're at 1, you can jump to 1 with the same probability as you jump from -1 to -1. So this is exponential beta divided by exponential minus beta plus exponential beta. And since you're jumping from 1 to 1 with this probability, this means that you jump from 1 to -1 with that probability. So this is a discrete time Markov chain, which is, of course, aperiodic, because you may jump from a point to itself, and it's also irreducible, well, because you may jump from 1 to -1 and from -1 to 1. So it's a discrete time Markov chain which is aperiodic and irreducible. The stationary state for this measure, it's very simple to obtain. What I claim is that pi of -1 equal that the uniform measure is stationary for this Markov chain. And in order to check that indeed this measure pi, it's the unique, we know that irreducible chain have a unique stationary state. Well, what I claim is that pi is the unique stationary state of that chain. And in order to prove that, well, we just need to check the detailed balance condition. The detailed balance condition is to say that if the probability that you are at -1 times the probability that you jump from -1 to 1, it's equal to the probability that you are at 1 times the probability that you jump from 1 to -1. Well, let's see that pi defined in this way indeed satisfies the detailed balance condition. You see that since the measure is stationary, the probability of 1 and -1 cancel. So what we need to check is that P is symmetric. And indeed, P is symmetric because we have seen that the probability to jump from 1 to -1 is equal to the probability to jump from -1 to 1. Therefore, the uniform measure, it's indeed the stationary state. So what is the matrix, the transition matrix of this Markov chain? So remember, the transition matrix, it's a matrix whose entries are PAB, where A it's -1, 1, and B it's 1, -1, which represents what is the probability for this Markov chain to jump from A to B. So we have them written here. So P is a matrix. And what are the entries? So say that our state space here, it's -1, 1. So we have at position 1, 1, the probability to jump from -1 to -1. And this, we have seen, it's given by this exponential. So let me write this as exponential beta, exponential minus beta, exponential minus beta, exponential beta, and we'll divide that by exponential beta plus exponential minus beta. So what I claim is that the transition matrix is given by this matrix. So let's check. So here, as I said, position -1, 1, we should have the probability to jump from -1 to -1, but the probability to jump from -1 to -1 is given by this expression, and this is exactly what appears here. And then, in this position, we have the probability to jump from -1 to 1, which is given by this ratio, and this is exactly what I have here. Then, the probability here, you have the probability to jump from 1 to -1, which is given by this expression, and this is exactly what we have here. And finally, here we have the probability to jump from 1 to 1, which is given by this ratio, which is what appears here. So we have thus defined this transition matrix P, and I will represent these terms by P, as I said. So P minus 1, 1 would be the probability to jump from minus 1 to 1. So this term here, which is exponential minus beta, divided by exponential beta plus exponential minus beta. And in the same way, you have P minus 1 minus 1, P1 minus 1, P1, 1. Right? Now, let me erase this, since we have now the expression of this matrix given by this expression. So let me just recall that we introduced PAB, where A and B are equal to minus 1 or 1, as the probability for that chain to jump from A to B. A and B are minus 1, 1 both, so they belong to this set. So now, instead of writing AB, let me write that as sigma z plus 1. And again, sigma z, so now I'm just using this notation. Sigma z, it's either minus 1 or plus 1. Sigma z plus 1 also, it's minus 1 plus 1. And let me observe that I can write this expression as exponential minus beta sigma z, or sigma z plus 1, I'm sorry, and plus, divided by exponential minus beta plus exponential beta. So I claim that I can write this jump probability, so the probability to jump from sigma z to sigma z plus 1, or to jump from A to B, if you wish, where AB or sigma z plus 1 are elements from minus 1, 1, as this equation. So let's check that. Well, we have to check 4 possibilities. Let's first consider the case in which both sigmas take the value minus 1. So in this case, we are jumping from minus 1 to 1, and this is given by exponential beta divided by exponential beta plus exponential minus beta. And this is exactly what we get here, because since both are equal to minus 1, this product is 1, and what we get, it's indeed exponential beta plus exponential minus beta. So now let's check the case in which we have minus 1 plus 1. We have here the formula for these probabilities given by exponential minus beta divided by that. And this is exactly what we get here, because now the product, sigma z plus 1, it's minus 1. And, well, just to complete the picture, now let's consider the case plus 1 minus 1. So here again, we are jumping from plus 1 minus 1, so this is the term. And this is exactly what we get here, because the product is minus 1. And in the final case in which both are equal to plus 1, we are here. And this is exactly what we get here, because this product is equal to plus 1. So we have that formula for the Markov chain I just introduced. So you see what we have here are exactly these probability, provided we divide each expression by exponential minus beta plus exponential beta. So this is what we will do here. I will take this formula, and I will divide and multiply each term by exponential minus beta plus exponential beta. So how many terms do we have? Well, here we have 2n terms, because if you go from minus n up to n, you have 2n plus 1 terms, but now you're going to up to n minus 1, so you have 2n terms. Here you have an extra term, and here another one. So this is actually equal to exponential minus beta plus exponential beta to the power 2n plus 2. And this is exactly, if you remember my claim, this is exactly the first expression which appears in the formula for the partition function. And now once we did that, we can replace each of these terms by this transition probability. So let me rewrite it here. So this sum, it's equal to the first term, which is exponential minus beta plus exponential beta to the power 2n plus 2. And now times the sum. And here I'm doing a sum for all configurations in minus 1 in omega n. So this is taking a sum over all sigma n, sigma minus n plus 1, up to sigma n, belonging to each one belonging to minus 1, 1. So I'm performing, saying that I'm summing over all configuration is the same thing as saying that I'm summing over all sigma minus n in minus 1, 1, all sigma minus n plus 1 in minus 1, 1, all sigma n in minus 1, 1. And what we have here, now I will replace each of these expressions, each of these ratios by p. So what we have here is the p of minus n plus 1 sigma minus n. So eta minus n plus 1 sigma minus n. So this is the first one. Then we have a product for z between minus n and minus 1 of the probability of sigma z plus 1, and then the probability of jumping from sigma n to to eta n plus 1. So this is exactly our formula for the partition function. So we expressed our partition function in terms of these jump probabilities of a Markov chain, a two-state Markov chain. That's very nice, because now you can see that what we have here is, well, you're starting from minus n, eta minus n plus 1, so this state, which is either 1 or minus 1, and you're jumping to sigma minus n, but you're summing over all possible jumps, and then you're summing from sigma minus n to sigma minus n plus 1, from sigma minus n plus 1 to sigma minus n plus 2, and so on, until you jump from sigma n minus 1 to sigma n, and from sigma n to eta n plus 1, and you're summing over all possible intermediate points. So this means that this sum is actually equal to the probability that you jump from minus n plus 1 to, from eta minus n plus 1 to eta n plus 1 in 2n plus 2 jumps, if I'm correct. So what I claim is that this is equal to this expression times the probability that in two steps you jump from eta minus n plus 1 to eta n plus 1. So here, this is just, you have a matrix here, so you're taking the power of this matrix, so the 2n plus 2 power of that matrix, which I'm representing in this way, and this corresponds to the probability that you jump from this configuration, from this state to that state, in 2n plus 2 steps. Right? If you want to compute this probability, what you'll do, it's, let's say, remember that if I want to compute p A, B is the probability that you jump from A to B. If I want what is the probability that starting from A, let me call this Markov, let me represent this discrete time Markov chain by xt. So t larger or equal to 0. So what is the probability? So this probability, it's the probability that starting from A you jump at time 1 to B. But now if I want to compute what is the probability that I jump in 2 steps from A to B, I will write that as a sum over all, let's call gamma between -1 and 1, so taking the value either -1 or 1 of the probability that at time 1 I am at gamma, and at time 2 I am at B, and this is the probability to jump from A to gamma times the probability to jump from gamma to B, and this is exactly P to AB. So you see that if you iterate this relation, what you get is that the power n of P computed at AB gives you the probability to be at time n at B starting from A, and this is exactly what we wrote here. What appeared here, it's a sum over all possible paths from eta minus n plus 1 to eta n plus 1 in 2n plus 2 steps, because, well, how many terms we have here? As we said, we have 1 term here, we have two n terms here, and we have 1 term here. So there are 2n plus 2 terms, and this is exactly to the power 2. We have 2 terms. So since there are 2n plus 2 terms, we have a power 2n plus 2. So this provides you a very simple formula for the partition function. We just proved that the partition function is given by this very simple expression. And so this is our constant alpha n, which appears in the statement of the lemma, and what remains to be proved in order to complete the proof of the lemma is that alpha n converges to 1/2. But we have seen that this chain, it's periodic, it's irreducible, and so we know that for all A and B, the limit as n converge to plus infinity of Pn A B, it's equal to pi of B, where pi is the stationary state, unique stationary state. So this is a basic result about Markov chain. If you have an irreducible aperiodic chain in a finite state space, you know that starting from any point, the probability that you're at B at some time n, as n converges to infinity, converges to the stationary state. And in our case, the stationary state we have seen is the uniform measure, so it's 1/2. And this does not depend on A and B. Therefore, as n tends to infinity, this expression indeed will converge to 1/2, and this completes the proof of the lemma. So now we are very close to the end. Let's prove the theorem using this lemma. So what we want to study is the asymptotic behavior of this probability. So what is the probability that sigma 0 is equal to -1? Well, this is a sum over all configuration sigma in omega n such that sigma 0 is equal to -1 of the probability of sigma. But the probability of sigma, it's given by 1 over the partition function, which are represented by eta and beta. now a sum over all configurations which at 0 are equal to -1 of exponential minus beta h eta n of sigma. By the lemma, I can replace z by this expression, so I have 1 over exponential minus beta plus exponential beta to the power 2n plus 2 times alpha n. And now let me rewrite this sum by using our representation. So in our representation, what we had, it's exponential beta eta minus n plus 1 sigma minus n. Then the product of, so I will just write the product as exponential beta sigma z plus 1 from z running from minus n to n minus 1, and the last term, exponential beta sigma n eta n plus 1. So this is the expression, but now mind, the sum runs to all sigma which at 0 are equal to -1. So we have here a special value for z, which is z equal to 0. So I will rewrite this as a sum from n to -1 of exponential beta sigma z plus 1. So in the last term, at -1, we have here -1, 0. So let me write that as -2. And here, let me introduce beta sigma -1 sigma 0. So I will write it sigma 0, though I know that sigma 0 is equal to -1, but I will write it this way. Then we have exponential beta sigma 0 sigma 1. The product now running from 1 up to n minus 1 of exponential beta sigma z plus 1. And the last term, exponential beta sigma n eta n plus 1. And if you compare to what we did before, and I'm missing, no, okay. So if I place this term here, exponential beta eta minus n plus 1 sigma minus n, you see that in this piece, so since I'm fixing sigma 0 to be -1, so this is just to remember that this expression it's -1 and this expression it's -1. It's fixed to be -1. And what we are really summing over, we are summing between of sigma minus n up to sigma 1 and from sigma 1 up to sigma n. So sigma 0 it's kept fixed to be -1, and we are summing over all the other vertices. And what I wanted to observe is that if you remember the previous proof, what we have is that we have exactly the same expression as we had before. We have here, we start from a configuration, eta minus n plus 1. We see all possible jumps, and until we reach a configuration -1. So let me call eta 0, say, to be -1. And let me replace sigma 0 by eta 0. Here, and also here. So since sigma 0 is equal to -1, I just replaced sigma 0 by -1, and let me represent -1 by eta 0. And also here a product in which we start from a configuration, we jump over all possible paths, and then we reach a configuration. So let me go back here. Since I'm summing over all sigmas in omega n, which at 0 are equal to -1. This is equivalent to say that I'm summing over all sigma minus n taking the value plus -1 up to sigma -1 taking the two values, then sigma 1 taking the two values, and sigma n taking the two values. You see that here, the first part, the sides which appear, the z's which appear, are those between -n and -1. So the sides 1 up to n do not appear here. While in this second term, only the sides between 1 and n appear, but not the sides between -n and -1. So I can rewrite this sum as a product of two sums. So in the first sum, I'm summing sigma minus n, all possible values of sigma n up to sigma -1. And here, we have a sum with all possible values of sigma 1 up to sigma n. Once you do that, what you see is that this is exactly the partition function, but with boundary conditions -n plus 1. Well, in the box, -n -1. So the first one is the partition function between -n and -1 with boundary conditions eta 0 and eta minus n plus 1, while the second one, it's the partition function on the box 1n minus 1, 1n, I'm sorry, with boundary conditions eta 0 and eta n plus 1. So my first expression, if I take in the first expression n plus 1 for the first one and then n plus 1 for the first one, you see that I can rewrite it as, so let me erase this first line and to continue my computation, saying that this is equal to, so I'll take a piece here, so that will be 1, so I have 1 over alpha n, then 1 over exponential minus beta plus exponential beta to the power n plus 1, the sum over sigma minus n up to sigma minus 1 of this expression. I don't have the energy to write it, so let me call that star. So this is star, which is exponential beta, this product times this product times this term. And then I'll take the second piece of exponential minus beta plus exponential beta to the power n plus 1, and a sum from sigma 1 up to sigma n of triangle, where triangle is this expression. Now, how many terms do I have here? Well, I'm starting from minus n, and I'm reaching 0, so I have n plus 1 terms, and this is exactly the power which appears here. And exactly in the same way, here I'm starting from 1 and I'm reaching n plus 1, so I also have n plus 1 terms, and this is exactly what appears here. So if I take each of these expressions and I divide them by this denominator, by exponential minus beta plus exponential beta, I have one, I can use 1 for each of these terms, exactly 1. And in this way, by dividing these expressions by exponential minus beta plus exponential beta, I can replace these exponentials by the p. And this is what I will do now. So what I'm doing is that I have still 1 over alpha n. And so I'm taking here, I have n plus 1 terms. So I'm dividing each of these terms by this exponential minus beta plus exponential beta. And by doing that, what appears here are p. So this is equal to the sum from minus n, sigma minus n to sigma minus 1 of p eta minus n plus 1 sigma minus n times the product from minus n to minus 2 of p sigma z plus 1 times p of sigma minus 1 eta 0, which is minus 1, so I can write it now as minus 1. And in the same way, the second sum will be the sum over sigma 1 up to sigma n of p minus 1 sigma 1 times the product from 1 up to n minus 1 of p sigma z plus 1 times p sigma n minus 1 eta n. Sigma n eta n plus 1. Right? This is exactly what I get when I divide each of these terms by this sum. So here you see that I'm repeating the computation we did in the proof of lemma. It could be much faster, but I want to present all details in this computation. And so again, by summing over all possible values of sigma minus n plus 1 up to sigma minus 1, what I get is that this expression, the sum, it's equal to the probability. You start from eta minus n plus 1, and you end at minus 1. And in how many steps? Well, you have here minus 1, you go up to minus n plus 1, so this is n plus 1, which I can write as a superscript saying that, well, this is the n plus 1 power of the matrix P computed at these two values, or below as it's usual. And here I have the same probability, but now you start from minus 1 and you reach eta n plus 1. And again, you go from 1 to n plus 1, so there are n plus 1 jumps, and this gives you n plus 1 here. So what we proved is that this probability, so the probability which I started from, which is the probability that with boundary conditions eta, the probability that the spin at 0 is equal to minus 1 can be written in this way. So alpha n, it's a sequence which converges to 1/2, and we have here the transition probability of a very simple two-state Markov chain. Now, since this Markov chain, we used already this argument, since this Markov chain is aperiodic and irreducible, and since the stationary state it's the uniform measure, whatever eta, this will converge. This sequence will converge to 1/2. This sequence will converge to 1/2. And since alpha n, it's also converging to 1/2, this product will converge to 1/2, as I claimed. So this is exactly the statement of the theorem, and that completes the proof of the fact that in dimension 1, the Ising model has no phase transition, in the sense that whatever the inverse of the temperature you choose, the origin does not feel the influence of the boundary. And we'll see in the next lecture that in dimension 2, and higher, the picture is completely different. There will, for very large beta, we'll show that for very large beta, this probability is strictly smaller than 1/2 if you take a periodic boundary condition to be equal to +1. So if you take square with boundary condition equal to +1, what we will show is that if beta is sufficiently large, then this probability will converge to something which is strictly less than 1/2. While if beta is less than a value, so if beta is sufficiently small, then this probability converges to 1/2, and therefore we have two qualitatively different behavior according to the temperature. But this is the content of the next lecture.